1.4 is the tangent and a velocity problem. So we're going to relate, right, the tangents of a graph and how could that be used in application problems. In geometry, we learned that the tangent is basically with a circle, right? The tangent is a a line that passes through any point on the circle only once. But however, that definition does not satisfy on other curve. Right? Like giving to you an example right here, if you have a polynomial, right, curve, something like this, a wave, and if you draw a tangent line to a point, then that tangent line passes through on other part of it. But what we are interested in is we are interested in only, a certain interval. Within a certain interval, what is the tangent line of that particular point? It's going to be. Okay. So once again, in geometry, the way that we learn is what a tangent line passes through what? A circle. Tangent line is a line that passes through a circle only once, right? Touch it, basically, but not in order. So in order to talk about the tangent line, right, in a certain interval of other graphs, what we want to do is we want to start talking about the secant line. And from this secant lines, how can we approach and then being able to compute or estimate what is the slope of the tangent line is going to be? Okay. The reason why is because we know that to talk about an equation of a line, any equation of a line, we need to have a slope, right? And to get the slope, I need 2 points. But the tangent line is only what? Touching to 1 point. That's what we are looking at. So looking at this parabola, right? And we want to find out, right, the tangent line, the slope of the tangent line at a point P. So the point P is 0, 2, which is right here, this point. And if we talk about tangent line of this point, that's basically we are looking at a line, right? We are looking at a line that simply just touch it there. No other points. Okay. So if we are only touching 1 point, then there's no way that you will be able to find out the slope of this tangent line. Because the slope formula, right? The slope formula is y equal to m equal to y2 minus y1 over x2 minus x1, right? We need 2 points. So what we're going to do is we're going to start from a secant line and approximating the slope of this, using the slope of the secant line to approximate. For example, this is the point P. I'm going to say that here's my another point. All right, here's my other points, Q. And if I connect these 2 points together, that will give me a secant line. And we find out the slope of the secant line. My graph is not good. It should be a straight line. I cannot draw it. Okay, make sure you use the straight edge to continue from it. So if I talk about the slope of the secant line, and this is going to be way off, right, from this tangent line, the slope of the tangent line that we want to look for. But however, what we can do is this. If I move this point Q closer and closer to P, meaning if I move the point Q around right here, and then the slope is much closer. The slope of the secant line PQ is a little bit closer to what? The slope of the tangent line now. And if I move this point Q very, very close to P, then these two lines are, just a tiny bit of slanting difference now, meaning what? Their slope is what? Much closer. So what we want to do is we want to find out a serial value to predict what is this slope of the tangent line is going to be. And I'm giving you a chart right here, right, of the prediction point. So how do we compute that? First, I want to find out, right, my point Q that is at one what? So we need to find out my y is of 1 and plug it into the formula x squared plus 2x plus 2. So that will be 1 squared plus 2 times 1 plus 2. So which is going to give us what? 5 right here. Right? So that's the very first point Q that I use. So it'll be 1 and then 5. And then what I'm going to do is I'm going to find out the slope of the secant line, right, which is PQ. Now I'm talking about this point now. My Q is 1, 5. Right? My Q is 1 point way up here. So I'm trying to look at the slope of this PQ, this point right here. Okay? Draw a line like this. So what is the slope? That's what we are looking at. So to find out the slope of PQ, that is basically what? Y2 minus Y1 over X2 minus X1. The Y coordinate of my point Q is 5. And then the Y coordinate of the P is what? 2. And then divided by X coordinate of my Y, my Q, point Q is 1, X coordinate of P is 0, which is gonna be what? 3. So therefore I got my slope is 3. So you find out the same way, right? For the points and the slope. Now I move my point Q to what? 0.5. And notice that where we're trying to reach, we're trying to get as close as what? The point P, which is my X coordinate of P is 0. So that's why my point Q is getting closer to 0 when I put it down 0.5. And then 0.1, 0.5, 0.05, 0.01, 0.005. And notice that the secant line that I draw, right, PQ, is getting closer and closer to what? The X coordinate 0. And what happened to the slope of the secant line? Take a look at this. 3, 2.5, 2.1, 2.05, 2.01, and 2.005, which seems like as the X coordinate of the Q is getting closer to 0, the slope of the secant line is approaching to what? 2. That's my estimation. So what I can do is I can sort of estimate that, hey, the slope of the tangent line, probably that is 2. All right. That's the estimations. And this is a very important idea. This idea is going to lead us into next sections, which is the main core of this chapter 1 in Cal 1. And then it follow everything's after that. Now, notice that this time for this first diagram, I'm using my point Q, right, to be getting closer and closer to point P from the right side. And the prediction that I got from the slope of the tangent line is 2. Would that be the same if I move my Q, right, approach Q to point P from the left hand side. So here's my P, and if I move my Q from the left hand side, for example, starting from here and then getting what? Closer and closer to P. Will the predictions of the tangent, the slope of the tangent line will be the same or not? So we look at right here on the chart. My first Q x coordinate is -1, which is right here. This is the point that we are talking about. And my y coordinate is 1. And the slope of the secant line is PQ is 1. And as we move closer, half, 0.1, and then 0.001, very, very close to this when x is 0 from the left-hand side. Now you see that the point Q is approaching from the left-hand side to P. And we got 0.5, 0.9, 0.95, 0.99, 0.95. And then as you can see, that is what? Again, going to what? 2. So since from the left-hand side and then the right-hand side are estimations, right, lead us to approaching to the same number, and we can sort of like think about, oh, okay, my guess will be what? 2 for the slope of the tangent line at this particular point on this particular parabola. Okay. So the key thing is we cannot find out the slope of the tangent lines with one point, right? And the tangent line by definitions is it will touch the graph only at once. Yes, it is true that not necessarily all the cases like that, but however, in this case, if you can see that, right? If the tangent line, if you continue, it will never touch with the graph on another point at all. So we won't be able to find that. So here's the idea how to find out the slope of the tangent. And what is this gonna lead us is, to talk about certain things that we are very interested in for like a lot of application problems. First, let's recall on what is the average velocity. If we have a position functions with the times, and let's say the graph of the position functions that we have, okay, is something like this. Let's say this is the position functions. Yes. And we know that if we have, here's the first time, right? And here's the second times slot. The change in position divided by the time elapsed, that is basically what? Average velocity. That's something that we learn. And from the graph, if you look at it, this change in position divided by change in time elapsed, this average velocity is nothing but what? The slope of the secant line that we were talking about earlier. So the interpretations that we can get, right? One interpretation that we can get right here is we can talk about the slope of the secant line on the position functions at in the same certain time interval. That is basically talking about what? Average velocity. Now, what we want in most of the times in this kind of situation, this kind of application problem, we don't want to talk about within the time interval. A lot of times what we want is what is the velocity at that time, particular times. Okay. So if you look at this point, what is the velocity at this point, which is the rate of change at that particular point? That is what we are trying to predict on the previous example, which is the slope of the tangent line. So now, in earlier example, you might be thinking, why do we need this, like, slope of the tangent line? It has a lot of application to it. This is one of the examples that I'm giving to you. What is the velocity at that particular point, which is instantaneous velocity, right? So that's how we can relate it. So the slope of tangent line, right, that is simply can interpret it as instantaneous velocity at a particular point. And this instantaneous velocity is not only used in the position functions. We can talk about instantaneous rate of change. All right. So what's basically like, what is a rate of change of a chemicals in that particular moment? Sometimes it is important. Right? So this is the idea that we want to understand and introduce in this sections. And I'm giving to you, an example with position functions on this. And this is a problem that we used to do a lot in algebra, right? A rocket is throwing upwards at the planet Mars, and the initial velocity with 10 meters per second, and its height in meters per second later is given by this function h of t is equal to 10t minus 1.86 t squared. Part A asks us to find out the average velocity on a certain time interval. Right? And then we're going to use that to predict, right, what is the instantaneous velocity might be at t equal to 1 second. Notice that the way that we do is what? On a time interval in part A, the time interval that given to you as what? 1 minute, 1 second, and then what? 1.1 second. And then it's getting closer to 1 second, which is 1.01 second, 1.001 seconds. And let's talk about how the rate of change is changing. So part A, for the time interval 1 second to 1.1 seconds, what is the average velocity? Okay. So average velocity in this case is change in position minus, right, change in positions over change in the time ellipse. So what you can do is you can use a calculator to compute that. And on the test, you don't need to show me every single step, right? But at least you need to show me the formula, change in positions, and then you can use a calculator to compute it and give me the final answer if you wanted to. But make sure you do that correctly, otherwise I won't be able to give you credits. So 0.10 times what's 1.1 minus 1.86 times what's 1.1 squared. Right? And then you use this value, right, to subtract with what? 1. So I can basically say that this is the way that you can do. Minus and open parentheses. You can copy down the whole thing and close parentheses, but go back and then change it in your calculator These are just one. Oh, I made a mistake. So that's one way to do it. If you have a TI calculator, is even better. What you can do is you can do y equal to, and type in the functions, which is 10. Okay, type in the functions, 10x minus 1.86 x squared. And then what you can do is you can go to table, right, and then table sets. So second table set, and you can start with, 1.1. You can start from 1 and then increment the 0.1. And then you go to table with values. And you can see that 1 is 8.14, 1.1 is 8.7494, and you can subtract those two values, right, using the calculator. So however you want to compute it is fine, right? But make sure you compute it correctly and give me the final answer correctly. So in this case, the final answer is approximately not approximately, will be exact, 6.094. And what we need to do is we need to use this for 3 times, which is the second one. We want to find out the time ellipse in 1 through 1.01. Again, that will be average velocity, h of 1.01 minus h of 1 divided by 1.01 minus 1. And the next one will be time ellipse of 1 to 1.001, right? And then the average velocity in this case will be h of 1.001 minus h of 1, which is 1.001 minus 1. So go ahead, pause it, and then use your calculator, and then find out if we get the same answer or not. So for this, I got my answer to be 6.2614. And the next one, I got 6.27814. So from here, right, from these 3 parts, our predictions for part B, the estimating the instantaneous velocity at t equal to 1. So I would say that instantaneous velocity at 1, maybe approximately 6.3, I would say, meter per second, rounded to 1 decimal place, because as you can see that it's getting larger and larger and larger, right? And you can try it out a couple moles, but it's really up to you. We are estimating. So at this point, that's all we can do until we have a solid, theoretical idea to approach on it, which is the main core of this chapter 1 and 2 ideas. And this is what I want to point out in these sections, right? And what is a secant lines and what is a tangent line that we learned before, and how can we use that to talk about the application problems in a prediction sense, right? Because at this point we can only predict and estimate. And the homework for these sessions is given to you 1 through 7 odd, not a lot. Just try to get the idea of this, right? And this is the end of 1.4.